Hello everyone, and welcome to Semiconductor News Decoded. I'm Ty, and I've spent 31 years inside the semiconductor industry. Today's topic? Rigaku and imec joining forces to accelerate next-generation metrology for advanced chips. Let me walk you through what's actually going on and why this matters. As always, let me explain this like you're hearing about semiconductors for the very first time. I'll keep the technical jargon to a minimum and lean on everyday analogies. So if you're a specialist watching, please bear with me on the simplifications, just for the early scenes. Here's the news in one sentence. A master craftsman who builds ultra-precise X-ray inspection machines is teaming up with the world's most advanced confectionery research lab to develop an even more precise inspection system together. And what are they inspecting? Cakes. Specifically, the most complex kind of cake imaginable, mille-feuille pastries with dozens of paper-thin layers stacked perfectly on top of each other. The mille-feuille this factory produces today has many times more layers than it used to. You simply can't tell from the outside whether the inside is properly baked, whether the layers are stacked cleanly, or whether tiny air bubbles have snuck in between them. And yet, before shipping, the factory absolutely has to verify the internal condition of every batch. This has become a real headache for modern pastry factories. The traditional method was simple. Cut one open and take a look. Slice it with a knife, expose the cross-section, and inspect it visually. But here's the obvious problem. Once you cut a cake, you can't sell it. And inspecting just one cake doesn't really tell you what's happening across the whole production run. Cutting also takes time. In a factory that makes thousands of cakes a day, this approach just couldn't keep up. This is where our craftsman's X-ray inspection machine comes in. Without cutting the cake at all, you simply shine X-rays through it from outside, and you can see everything. Layer thickness, density, trapped air bubbles, even subtle distortions inside. And you can inspect multiple cakes at once. Just by eliminating that cutting step, the entire efficiency of the factory transforms. That said, this inspection machine still has its challenges. Reading what's going on inside the layers from raw X-ray signals takes heavy computation, and you don't get an answer instantly. And interpreting what each signal actually means requires years of experience and a deep accumulated database. Right now, this tool sits mostly in the recipe development stage, used to figure out the optimal baking conditions. But the more it gets used, the more data piles up, and the faster the system can recognize this signal pattern means this internal state. Once that happens, even high-volume production lines come into play. That wraps up the absolute beginner version. The point is simple. X-ray inspection looks inside without destroying the product, but it's still slow today, and it gets faster only as data accumulates. From here on, I'll switch into my 31 years in the industry mode and walk you through what's actually happening in the real semiconductor world. That said, this inspection machine still has its challenges. Reading what's going on inside the layers from raw X-ray signals takes heavy computation, and you don't get an answer instantly. And interpreting what each signal actually means requires years of experience and a deep accumulated database. Right now, this tool sits mostly in the recipe development stage, used to figure out the optimal baking conditions. But the more it gets used, the more data piles up, and the faster the system can recognize this signal pattern means this internal state. Once that happens, even high-volume production lines come into play. That wraps up the absolute beginner version. The point is simple. X-ray inspection looks inside without destroying the product, but it's still slow today, and it gets faster only as data accumulates. From here on, I'll switch into my 31 years in the industry mode and walk you through what's actually happening in the real semiconductor world. Rigaku's core strength is non-destructive measurement of internal structure. In advanced semiconductors today, structures are getting more and more three-dimensional. GAA transistors, CFET, 3D DRAM, hybrid bonding, and so on. Just looking at the surface isn't enough anymore. Things like thin film thickness deep inside the stack, composition, mechanical stress, bonding quality, and voids, all of these now directly determine device performance and yield. The classic tool for looking inside is TEM, transmission electron microscopy. TEM is still in active use today, but it has serious downsides. It's slow, sample preparation is painful, it destroys the wafer, and fundamentally, it's a single-point measurement. X-ray metrology, by contrast, can measure the internal structure across an entire wafer, statistically, without destroying anything. During process development and condition tuning, this difference is enormous. And the barriers to entry in this space are extraordinarily high. To do X-ray metrology, you need everything at once: a high-performance X-ray source, precision optics, highly sensitive detectors, robust analytical models that interpret scattering and diffraction data, and deep knowledge of semiconductor processes. Images don't just pop out. You reconstruct the internal structure backwards from the signal. So even though Rigaku is technically an equipment maker, they're really physicists at heart. That depth of physics expertise is exactly Rigaku's strength. Rigaku projects that by 2030, the market for metrology equipment targeting advanced AI semiconductors will reach roughly $1 billion, and they're aiming to capture 50% of that share. That's more than 10 times the size of today's market. It's an aggressive number, but it also tells you just how confident they are in the growth of this segment. So where can Rigaku's X-ray metrology deliver immediate value right now? Process development and condition tuning. As engineers tweak etch parameters, anneal conditions, and deposition recipes, they can monitor how the recess depth changes, how film thickness or composition shifts, and how the bonding behaves, all without destroying a single wafer. For this use case, I think X-ray metrology is already quite effective today. But there's a separate question. Will it actually be used in volume production? Take wafer defect inspection and classification. That domain is dominated overwhelmingly by KLA, the American equipment giant. KLA's strength in high-volume production comes down to one word: speed. On a production line, 4 things have to come together. You must be able to measure fast, classify automatically, run inline, and correlate the results directly with yield. Without all 4, the tool isn't practical. X-ray analysis still takes time and depends heavily on its analytical models. We're not yet in the measure it and get an instant answer world. Here's another critical point about defect analysis and yield improvement. From my own years on the production floor, the single hardest thing, by far, is deciding where to look when a defect shows up. The act of narrowing down which signal, which structure, which process step you should even check to find the answer, that question itself is the toughest one in this entire game. And even KLA, which dominates this narrowing down problem today, wasn't all-powerful from day one. As I recall, the earliest KLA tools could only tell you the size and the coordinates of surface particles. That alone, just we know where the particles are, was already a huge leap forward for the factory floor. From there, by patiently accumulating defect coordinates, sizes, process step data, electrical test results, and final yield numbers over many, many years, KLA gradually built up the knowledge to say this defect type really hurts yield, or this process condition produces that anomaly right there. In my view, KLA evolved from being a defect detection equipment maker into being fundamentally a yield learning company. There's another important move worth highlighting. On April 21st, Rigaku announced a strategic partnership with Onto Innovation. It's a large-scale capital alliance in which Onto Innovation will acquire roughly 27% of Rigaku shares, with the deal expected to close in the second half of 2026. The significance of the Onto partnership is huge. The fact that Onto is taking 27% of Rigaku says loud and clear that Onto values Rigaku's X-ray technology very highly. They're committing real capital precisely because they're convinced the value is genuinely there. Now, Rigaku are X-ray physicists at heart, but Onto's strength lies in optical metrology and AI-driven analytics. If you combine them, use optics to see wide and fast, use X-rays to see deep inside, and tie all of that data back to yield, you suddenly have a uniquely powerful stack. That's a different battlefield from the one KLA dominates, and it gives Rigaku a real shot at carving out a defensible position in deep internal structural measurement. Not a head-on collision with KLA, but rather competing at a depth that KLA simply isn't watching. Let me pull this all together. What Rigaku's partnership with imec really means goes far beyond ordinary joint research. As next-generation structures like GAA, CFET, and 3D DRAM keep growing more complex, the industry is forced to face one inescapable truth. Looking only at the surface isn't enough anymore. Rigaku's weapon of choice is non-destructive X-ray measurement of the internal structure. For process development and condition tuning, the ability to gather statistical, full-wafer data without destroying anything, unlike TEM, is a major strategic advantage. On the volume production side, however, the walls of speed and model accuracy are still very real. The Onto partnership is laying the groundwork to combine optical speed with X-ray depth and to accumulate data on a different battlefield from KLA's. And the sheer height of the entry barriers means that competition in this market won't open up to newcomers anytime soon. Only when technology, accumulated know-how, and proprietary data all three come together can Rigaku build a truly durable long-term position. The road is long, but they have started walking it, and they're walking it steadily.
Here's my own conclusion. I genuinely believe Rigaku's potential is real. But this is not a story about Rigaku becoming a must-have piece of volume production infrastructure overnight, the way KLA already is. The real path forward, the path that makes Rigaku truly powerful in the long run, runs first through process development, building track record there, and then patiently spinning the cycle of linking X-ray data back to yield outcomes, again and again. In that sense, the 3-year program with imec carries enormous significance as the starting point for exactly that kind of data accumulation. Rigaku's upside is high, but getting there demands years and steady, unglamorous effort. I, for one, plan to keep watching their journey closely.
That's all for today's Rigaku and imec episode of Semiconductor News Decoded. I'll keep bringing you semiconductor news and analysis, so if you found this video interesting, please like, subscribe, and I'll see you next time. Thanks for watching.